2 of the Attochem cost action. So initially in the program, we had 4 speakers in this session, but unfortunately, Violeta Petrovic had to cancel her talk, so we remain with 3. But well, I am sure that we will have 3 very interesting talks. The first presentation is of a Zdenek machine from the Charles University of Prague. It's a long title, but you will say it's Zdenek, but it's about R matrix.
That's correct. It's a long title. I realized it's the longest title in this conference, unfortunately.
So Zdenek, the floor is yours.
Yeah, thank you. All right. So first of all, it's a pleasure to be attending this meeting. It's a very nice meeting, and to have the opportunity to present the results of some of our latest developments. And I would like to thank the organizers for that. And let me begin. Okay, so the topic of my presentation is localization of secret states in multi-electron molecular R matrix calculations. So let me first begin by a brief motivation for this work. So there is an analogy that was proposed in a paper of De Oliveira from 2010 between photo excitation reactions and between reactions that are triggered by electron impact. So on the left, you can see an example of a reaction that can be triggered by a photon in a molecule. So the molecule is first excited to a bright pi star state, which induces some vibration dynamics in the molecule, and that can cause symmetry lowering that allows coupling between this blue state and the green state, which is repulsive along some reaction coordinate. However, this repulsive state crosses the neutral state. So this allows for the possibility of stabilization. Or, of course, if the reaction proceeds along the green curve, the molecule can dissociate. Now, the idea is that something similar is happening actually in electron collisions with molecules, where the process of dissociative electron attachment can take place. So we can visualize it similarly. So first, the electron is incoming with some energy and is trapped into a temporary negative ion, which is this pi star resonance. This induces some vibrational motion in the molecule, and that can cause symmetry lowering and a coupling of this resonance to another resonance state, which is this sigma star anion state that is repulsive along some reaction coordinate and can cause dissociation of the molecule. So we have again here 2 possibilities. So either the molecule is broken by the sigma star dissociative state, or auto-detachment can take place and the electron is leaving before the molecule is broken. So in both these cases, in the photo-induced reactions and electron-induced reactions, we have these simple molecular orbital picture sort of visualizations. So when electrons are either excited to or occupy some of these virtual orbitals. So in my talk, however, I will challenge the point of view on these electron-induced reactions somewhat. And I will ask whether our interpretation of these electron-induced reactions that are proceeding via this sigma star anion are accurate. And you may ask, well, why are you asking such a silly question? I mean, we have known this for a long time, that this is how these reactions often proceed. And I will show you that this is not so simple. So let's have a look at an example of dissociative electron attachment to formic acid. So when an electron is colliding with this molecule, dissociative electron attachment can take place, and that can leave behind a neutral hydrogen and a negatively charged fragment. Now, the question that we are asking is, what is this intermediate state that is mediating this reaction? Well, there are 2 theories were proposed to explain this. The first one, or theory 1, as I call it here, was of Gordon Gallup and Ilya Fabrikant from 2009. And it says that this is simple. as we just saw on the previous slide. So the electron is attacking the molecule. It attaches to some sigma star repulsive state, which is repulsive along the bond that's being broken. So that's simple. However, this resonance has some extreme properties, like it has a width of about 6 electron volts. So it's extremely short-lived. While there was a second theory proposed to explain the same process that was proposed by Tom Ressignon, actually a bit earlier in 2006. And it says, no, it's not so simple. Actually, the electron is attaching to a narrow shape resonance, which we all know is in this molecule, is present and is well known. But this resonance is causing some distortion of the molecular geometry. So like there are some bonds that are being extended and rotated. In particular, this CH bond rotates. And this apparently opens the pathway for the bond to be broken. So this OH bond to be broken. So here we see this potential energy curve of the resonance, which crosses the neutral along this reaction coordinate. Well, but which one of those theories is correct? Well, we have to ask the experiment to resolve this problem. And the experiments were done in a group of Michael Allan in 2013. And the winner is that the direct OH bond break is actually taking place. So it's the simplest mechanism. And well, how does the experiment determine that? Well, you deuterate this carbon position here, which prevents the out-of-plane motion that's necessary in the theory of Ressignon to take place. So if you deuterate it, well, this out-of-plane motion is much slower because deuterium is much heavier. And you see that indeed the experiment shows that if you deuterate on this carbon position, the dissociative electron attachment cross-section is virtually unchanged. So indeed, there is very little distortion in the molecular geometry and the process is direct. However, there is a problem because this sigma star resonance that's been proposed has never been found by any ab initio calculations. And this is not true not only in formic acid, but also in other molecules like uracil, where the same mechanism is thought to take place. Well, so why is this such a problem? Why could we not find this sigma star resonance? To understand this, we have to look at how we actually identify resonances in our computed data. So here's a couple of examples. So here is a cross-section for electron impact, electronic excitation of pyrimidine that we calculated, which is this black curve. And there is the experiment, which is this jagged red curve. And all these peaks here correspond to resonances. And we spend a lot of time trying to basically identify those resonances, make sure that these peaks really are resonances, that they are not some kind of other background scattering or anything like that. To do that, it's actually really difficult because you have to compute a lot of different data. You have to look at different observables like time delays, of course, eigenphase sums. You have to run models with different levels of complexity, etc. And sometimes you're still not sure. So characterization of resonances is difficult when the resonances are very broad, such as in the case of formic acid, or if the resonances have some mixed electronic character. Similar issues arise when you look at photoionization, which we did in CO2. And here are cross-sections and beta parameters for ionization into several lowest lying states of CO2. And well, some of these peaks that you see here are resonant, such as this really large broad peak in the cross-section for the C channel. That's the well-known mixed core-excited shape resonance. However, for example, this bump in the B state cross-section, that's actually non-resonant. Even though it looks like it could be resonance, it's actually an onset of P wave scattering. So we can put it in other terms, and we can realize that resonances are, in fact, solutions of the Schrödinger equation in the complex plane. So there's some energy in the complex plane where the resonance lives, and the closer it is to the real axis, the more prominent it is. So however, if it's far away, we don't really see it clearly. So it's almost like looking at the shadows on the wall, right? I mean, we look at the cross sections and we only can indirectly infer what's going on. So instead of looking at the shadows, we would like to look at the real thing, which is something like this, where we have on the bottom the actual complex energy plane, and all the points there correspond to resonance states, which are deep in the complex plane. And you see that indeed, if the point, the Sigurd state is close to the real energy axis, then it leads to a prominent bump in the cross-section, but not the other ones which are far away. So I'm going to talk about how we actually obtain this kind of level of analysis, where we can look at resonances in great detail and really analyze what's going on in the system. So first of all, resonances, virtual states and bound states are special, well, it's sort of one family of solutions of the Schrödinger equation, which are called the Sigurd states, which are defined by the outgoing boundary conditions at infinity with complex momentum. So these are solutions of the Schrödinger equation for complex energies or complex momenta, which obey purely outgoing boundary conditions. Now, there's a small complication, which is that these virtual states and resonances are actually exponentially diverging solutions, which makes it uneasy to handle in usual numerical methods. But there are, other methods that have been used other than the R matrix to calculate Sigurd states. But in fact, one of the first, I think one of the first methods that were used in ab initio calculations to localize Sigurd states were actually R matrix calculations already in 1988. And this was work that was done by Leslie Morgan and Phil Burke on hydrogen fluoride and diatomic molecules. So those were pioneering calculations. However, interestingly, this implementation has been lost and hasn't been used for, over 20 years. There are other methods that could be used also to find Sigurd states, such as exterior complex scaling, like was done, for example, for the giant resonance in xenon in the work of Chen et al. So how do we actually solve for the Sigurd states in R matrix? Well, before we get to Sigurd states, let's just try to look at how the R matrix method actually works, which was, I think, a question that a few people raised before. So I shall attempt a brief explanation. So let's say we have the simplest problem, like scattering from short-range potential. So here is our solution, the continuum wave function at some energy, which we'd like to obtain. How do we do that? Well, we realize that the whole problem can be split into two parts. One part, which is the inner region, that's the difficult part where the potential is non-zero. Then the outer part, which is simple, that's where the potential is zero. So because it's a differential equation, because Schrödinger equation is a differential equation, we can solve it separately in different parts of space and then join it at the boundary, which is called the R matrix sphere. So the simple solution is known explicitly, or at least its form is known explicitly. We know that in the outer region, it's some combination of the Bessel functions. Now, if we want to obtain the full solution, we have to match the inner solution with the outer solution on the R matrix sphere, and that's done, as you know, by just matching the amplitudes and its derivatives. Okay, so far so good. However, the main feature of the R matrix method is that it embeds the derivative boundary condition right into the differential equation. So this is the key point of the R matrix. So how we do it is that we add this term, which is called the block term, and that basically calculates the derivative of the wave function at the boundary. So we insert into the Schrödinger equation this term, which is, say, the derivative of the inner region wave function, and on the left-hand side and on the right-hand side, the derivative of the outer region wave function. By this, we ensure that the solution in the inner region automatically obeys the correct boundary conditions on the R matrix sphere. So we can now express the inner region solution using the Green's function of the Schrödinger equation applied to the right-hand side or to the source term, which is here. The key point is that the Green's function actually has an exact, or well, not exact, but an analytic dependence on energy. So this is a key point of the R matrix. While these states, psi k, are the so-called R matrix basis functions, which are obtained by diagonalizing the Hamiltonian in the inner region. So the last step that we have to make is to match the amplitudes of the solution from the inner region and the outer region. So we have now the expression for the inner region wave function in terms of the Green's function, and we just evaluate it at the boundary and set it equal to the outer region solution. So we get the fundamental equation of the R matrix. So this is the matching equation that's stated in every R matrix talk. So now that we have this, we can insert into this equation the known form of the outer region solution and express the unknown variable, which is the phase shift, basically, or the tangent of the phase shift. And we see that it's expressed in terms of the known outer region solutions and the so-called R matrix, which in this case is not an R matrix because it's a single channel problem, so it's only a function, but it's a function of energy that contains all the information about the inner region. So just to summarize, the R matrix is useful when the solution in the outer region part of space is known. The advantage of the R matrix method is that the complicated inner region problem is solved only once. And last but not least, the R matrix has an analytic dependence on energy. And this means that solutions for a large number of energies can be obtained very quickly, and including in the complex energy plane. As you heard earlier today, the R matrix, of course, has a multi-electron version, which is what we use. And Jimena and Jakub have done a great job at explaining what it does in detail for complicated targets. So just to reiterate, the inner region is defined by the extent of the charge density of the target molecule. The inner region problem solves the complicated multi-electron problem using techniques that are similar to quantum chemistry, essentially by configuration interaction. In the outer region, the electron is far away from the molecule. So we can imagine this process as just one particle, the electron, feeling some effective potential representing the molecule. So it's a one electron problem for an electron moving in some non-spherical potential. And we solve the whole problem by matching the inner and the outer region by the R matrix condition. And again, so in this case, if it's a multi-electron problem and multi-channel problem, the R becomes really a matrix. But it still has the same analytic dependence on energy, which is important to keep in mind. So now, how do we obtain the solutions for the Sigurd states? So these are the solutions for the complex energies. Well, as I said, as you can see, basically, the whole R matrix problem, or everything that depends on energy, is confined to the outer region. So we are only interested in the outer region problem when we are looking at Sigurd states. So the outer region problem is defined by this set of coupled channel radial equations with some coupling potentials. As Jakub mentioned earlier, when there is a Coulomb interaction, then that dominates, so these terms can be safely neglected. Similarly, if we have scattering from neutral molecules, then the dipolar interaction is the strongest, and we can remove it we can remove the coupling that's induced by it by diagonalization of the matrix of the dipolar couplings and the angular momentum. So now we know how to deal with the outer region problem. So we can compute the scattering states first. We just look at the scattering state. So in this problem, the scattering energy is fixed, and as in the simple one-dimensional problem, we are looking for the K matrix or the phase shifts that then completely describe the solution. So we just use the R matrix matching equation and get an equation for the K matrix. Now, when we look for Sigurd states, the task is reversed. We know what the boundary conditions are. These are defined by the outgoing wave boundary conditions. So there's no variability here, but we look for energy, a complex energy or complex momentum, such that the solution exists, which means that the matching condition of the R matrix has a solution. So it leads to the problem of finding solution to this matrix equation. So how do we do it in practice? In practice, this is a root search problem. So we have some function m of e, which is a determinant of the R matrix matching equation, and we look for its zeros. So if we plot it in the complex plane, what it looks like when we plot the absolute value in the complex momentum plane, we see this. So the function has a huge gradient, as you can see. So from the real axis to the complex axis, it changes magnitude by, about 20 orders of magnitude easily, when you move just a little bit away. So this means that any automatic search for poles, which are these dots here, would be very hard. So instead, what we do is we basically use more or less a brute force method. So we calculate this function, this m of e, on a very, very fine dense grid of momenta, and we just identify the poles as the local minima in this function. And I would like to reiterate that this is possible because the R matrix has an analytic dependence on energy. So that's why these calculations can be done for so many energies as is required. So now for some applications. So I will describe calculations for 3 molecules, which will then lead onto the problem that I described at the beginning. So first we will look at what the resonances look like in the simplest system, which is nitrogen molecule. Well, in a simple system such as nitrogen molecule, which has only short range interaction and contains a well-known pi star resonance. Then we will move on to collisions with H and CO, which is interesting because in this system, we know that there actually is a dissociative sigma star resonance, but the system has a dipolar, there is a dipole moment, and so there is a dipole interaction. Then we will move on to electron collisions with pyrrole, where the situation with resonance, with the sigma star resonance is unclear, because we are not sure whether the resonance is there, because previous calculations are inconclusive. So the situation in pyrrole is very similar to formic acid, uracil, and other molecules, but this molecule has an advantage that it has a very high symmetry, but it also contains a dipolar interaction. So let's have a look at the collisions with N2. So here I'm showing you several plots. So on top left, you see the cross sections for the scattering symmetry where the pi star resonance appears. And the cross sections are calculated as a function of the bond length. And on the bottom, you see the Siegert states as a function of the bond length in the complex energy plane. And the horizontal axis is aligned with the cross sections so that you see how the points correspond to what you see there. So this is basically these, as I was saying, these shadows that we see. So in the cross sections, we see the peaks, and that's a reflection of the pole in the complex energy plane. An equivalent picture is obtained when we look into the complex momentum plane. It's just that the trajectories look a bit different. So what we see here is that the resonance, which is here, actually does become a bound state as the bond is extended. And that's clear both from the complex energy plane and from the cross sections. So the resonance becomes narrower and the peak in the cross sections sharper, and it becomes a bound state. What we also note is that there is a large number of these very wide Siegert states. So this is a typical feature of every quantum scattering that was already shown in 1959. Now let's have a look at the electron collisions with H and CO. So here we see that we have again a resonance here, which is a sigma star type of resonance. And but we see that in the complex energy plane, it behaves rather differently. It does not become narrower, it actually becomes broader. So you see that it as the bond length between the hydrogen and the nitrogen is stretched, the resonance actually disappears in the continuum, but it does not become a bound state. The bound state appears actually as a completely disconnected state. It's disconnected from the trajectory of the resonance. And we also find that the molecule supports this so-called dipole bound state, which is a very weakly bound state by the dipole interaction. the fact that the resonance is disconnected from the valence bound state is a feature of the long-range dipole interaction. And this was shown by Estrada and Domke in 1984. So on the right, you see the equivalent picture of what I was just describing, and that's from the work of Zavadsky from 2018. So you see the potential curve of the neutral, and here is the resonance, which goes down in energy, but becomes wide as it's appeared close to the threshold. And then there is the bound state here. So finally, let's have a look at the electron collisions with Pyrrole. Pyrrole has a C2V symmetry.
One more minute, please.
Okay. So there are 4 symmetries, and you can see that there are quite a few resonance states here. So we see that there is a sigma star dissociative resonance. Sorry, that's not dissociative. It's a sigma star resonance that's high in energy, and then there are some narrow pi star resonances. What we are interested in is what happens when you change the bond, when you extend the bond between the hydrogen and the nitrogen. What you see is that this resonance actually is not dissociative at all, and that the resonance is disconnected from the valence bound state. So there is no sigma star resonance that becomes bound in the system. So there is a problem now. So we have this valence bound state, which leads to the dissociative electron attachment, but there is no curve that connects it to the continuum. So where is the sigma star orbital gone? We can do it by analyzing the so-called Dyson orbitals of the states that are involved. We can calculate what is the contribution of the sigma star orbital that we're looking for to the dipole bound state and the valence bound state. And we see that it's actually the dipole bound state which accumulates the contribution of the sigma star orbital, and that is then transferred to the valence bound state. And we can also see how the sigma star orbital is reflected in the continuum. And we see that there is a sigma star orbital that contributes to the continuum, which looks like as if there was a resonance, but there is no resonance, because we saw that in the calculations that there is no such resonance state. So in fact, this feature in the continuum is nothing else but a reflection of the dipole bound state that's present in the system. So our ab initio calculations are fine. It's only our interpretation of the process that was wrong. So there's also a question of what happens when the molecule does not support bound states. And it basically reduces to the fact that the dipole bound state is replaced by a virtual state. So it's actually a rather simple mechanism. However, the message of this talk is that when you look at, when you compute molecular orbitals, you have to be careful with their interpretation when you are trying to interpret unbound states. So dissociative sigma star orbitals may not represent resonance states. What was done in the calculations of Gallup et al. Was that it was used to parameterize in a Feshbach type method the dissociative electron attachment, but please do not call this state a resonance. It's your choice of basis. Okay, finally, the main point is that the dissociative electron attachment in polar molecules does not require resonance formation, but it's induced instead by a dipole bound or virtual states. So with this, I finish, and I would like to thank my collaborators, Jakub Benda, Thomas Meltzer, Karol Hofek, and Jimena for work on the codes, and Juraj Fedor for suggestions to look at Pyrrole. Thank you for your attention.
Thank you, Zdenek, for this very clear talk. Please, if you have questions, raise your virtual hands from the Zoom application. Do we have any questions? Yes, Nicholas, please.
Hi, can you hear me?
Yes.
Okay, cool. Yeah, I have a problem, and I wonder if your method can solve it. So let's say you have two resonances, and they are degenerate now. So they are really close. I mean, they have the same energy. So then they can, I mean, it's hard to define their width, because you can have like a free continuum coupling and so on. Can you treat that with your method?
Sure. Well, I guess the question is what kind of degeneracy it is. If it's a degeneracy in if there are different symmetries, but they just appear at the same energy, or if it's some kind of accidental degeneracy where they appear really at the same energy. I don't know.
The second one.
Sorry?
The second one. So same symmetry, but just accidental.
Yeah. I mean, they would then appear. What you're saying is that you have basically a double pole or something like that.
Yes.
Yeah, well, if it's a double pole, then it's complicated. But I would like to point out that if the resonances are only degenerate in their real energy but different width, then of course we can see that clearly from the complex plane, because of course in the complex plane they would appear at different points and they would be clearly separated. So actually, this method is something that can be used to distinguish between overlapping resonances. But
I see. But the issue is that to get those width, you need to be sure that we have this continuum coupling correctly and so on. This would be done correctly in the R matrix part, and your analysis won't mess up with this coupling.
No, sure it won't. No, it's all this is up initial calculations. So it would be possible to calculate those resonances. Yeah.
Oh, great. Okay, thank you.
Okay, any other questions? I do not see any hands. What if not? Just thank you, Zdenek, again for this nice talk. And our next speaker is András Csehi from the University of Debrecen. Please, András, the floor is yours.
Thank you. Can you hear me?
Yes, it's good.
And you can
le grappe dietro.
just let me share my. Okay, so can you see my slides?
Yes, if you can do it full screen, please.
Yes, okay, good.
Okay.
So
good, thanks.
Good. So first of all, I'd like to thank the organizers for the opportunity so that I can present some of our recent results on dynamic interference. In this talk, I'd like to demonstrate how we can trace strong field induced dynamics, rapid dynamics between bound states of atomic systems in the photoelectron spectrum, especially in the dynamic interference pattern. It is well known that in strong laser fields, the atomic and molecular levels are subjected to Stark shifts. And if the laser pulse supports many optical cycles, then the Stark shifts follow the pulse intensity envelope. And in this way, the electrons emitted at the rising edge of the pulse have the same energies as those emitted on the falling edge of the pulse. And due to this time difference or phase shift or phase difference, these electron amplitudes interfere, and this so-called dynamic interference occurs. This effect have been well studied over the past decade by several groups. Just to mention a few of them are listed here. And importantly, mostly the direct or one photon ionization have been considered and studied in detail. And it is also possible, the dynamic interference also occurs when resonance enhanced ionization happens. And this kind of process has attracted less interest over the years. So we really want to focus on resonance enhanced ionization and following dynamic interference to probe the dynamics of the system. Few words about the direct dynamic interference. They are used in short or high frequency and high intensity laser pulses in the XUV regime. And it was observed that below a certain intensity, the single photo peak, we observe single photo peak, but beyond a certain laser intensity, this single peak is replaced by a multi-peak pattern in the spectrum. And there are several milestones of this kind of effect. And mostly in the beginning, model ions have been studied, and later atomic hydrogen, atomic helium, and it was debated whether this dynamic interference occurs for ground state systems or not. And later it was clearly demonstrated that ground state atoms also exhibit dynamic interference. And especially it was emphasized that the appearance of dynamic interference can be considered as a signature of atomic stabilization. As I mentioned before, resonance enhanced multiphoton ionization also leads to dynamic interference, and in such a process, one can probe the Rabi dynamics between the resonantly coupled atomic states by another photon, which leads to ionization. So the situation when the bound-bound transition is induced by a single photon, namely 1+1 photon Rampey process, have been studied before, and to show that in this case the Stark shifts do not play a significant role. And so here we want to focus on situations when the dynamics, the Stark shift of the energy levels plays an important role. So we want to study such a process like the 2+1 photon Rampey process, where the Stark shifts play a crucial role. And basically everything I'm talking about today here can be found in this recently published paper. And as I told before, we want to focus on the 2+1 photon Rampey. Namely, we induce a 2-photon Rabi dynamics between two bound states of the atom, the lithium atom in this case, and probe this dynamics with a third photon that leads to ionization. So to do that, we develop a theory. We want to obtain a minimal model, a minimal three-state model, to understand the physics of this process. So in our treatment, the total wave function of the system is considered as shown here. Here we have the initial or the ground state, which is 2s for lithium. We have the resonance state, which is the 4s state for lithium. And we have the ionic states, which are labeled by epsilon, and these are populated after ionization. And we also have the so-called n-state manifold, which are the non-essential states, as they are not populated during the dynamics. They are far from resonance. That's why these states rapidly oscillate. And these include the bound state and also the continuum states as well. And so these are, even though they are not populated, they are important because, as we will see, they give rise to the Stark shifts of the essential states, the initial and the resonance states, for example. So it is important to include these states in the description. And of course, we plug this wave function form into the Schrödinger equation, and we end up with this coupled set of first-order differential equations for the population amplitudes. And here we have on the right side, the V is nothing but the interaction matrix element in the dipole approximation. So mu is the transition dipole, and epsilon, capital epsilon, is the linearly polarized Gaussian path. This has such a form in our study. This G is a Gaussian envelope, and omega is the central frequency, and gamma is kept constant if not stated otherwise. So we have this set of equations, which is, well, it can be difficult to solve because there are many states on the right side, and the same number of coupled equations. So we want to simplify this set of equations as much as possible, keeping the essence of the problem. And one can simplify this by invoking that certain couplings, certain TDMs are 0, or they can be neglected. So for example, the initial state is coupled to the M state. The M state manifold, the non-essential state, include the P states in this case, P states, because for example, the D states are not coupled to the S states. So due to the selection rules, these are the P states. And so here, for example, the coupling between the S states or the coupling between the P states is 0. So the ground state is coupled to the M state manifold only. And the direct ionization is neglected of the ground state because the photon energy we consider here is well below the ionization potential. But we checked it in multi-state calculations, and indeed this is justified, this kind of simplification. So there is no significant, notable ionization from the ground state directly. And the R state, the 4s state, is coupled to the non-essential state, and also ionization can occur from this state, of course. And here we have the M state manifold, which is coupled to the initial and resonance states. These states are coupled to these two states. And we have the ionic states, which are populated from the resonance state. And this is a much more simple form of the equation, which can be further simplified by invoking certain approximations known from the literature. For example, the so-called local approximation. In that approximation, we can substitute this term by this lossy term here, which is gamma is the rate for the ionization. So it describes the population loss of the R state, or by invoking the rotating wave approximation, we can simplify this term here. Here, omega 1 is the one photon Rabi frequency, basically the coupling to the continuum. And what we can do is the adiabatic elimination of these M state manifold, because as I told before, these M states are rapidly oscillating, so one can integrate this equation by parts, and after that we end up with this form, which can be plugged back into the first two equations here and here. And after doing that, these equations become much more simple, and we end up with a three-state equation, and the following form is obtained. So here the three states, and in the matrix we have the dynamic Stark shifts, these of the individual levels, which are time dependent, and we have the 2 photon Rabi frequency, the 1 photon Rabi frequency coupling to the continuum, and also the detuning. The delta is the 2 photon detuning, kept 0 in our study, and small delta is the 1 photon detuning in the continuum, and this UP is an important quantity, the ponderomotive shift of the continuum. This has been debated before, whether it is important or not. We will show its impact. So these Stark shifts and also the 2 photon Rabi frequency are calculated from the system stationary quantities like the dipoles and the transition frequencies, and it depends also on the laser frequency and follows the pulse intensity envelope. So we to do the dynamics, we need to calculate these or such kind of quantities in advance. The peak values has to be calculated from the system quantities. And yes, we did that, and for a certain laser intensity, for certain laser parameter set, I show you an example for the peak values of these quantities, and we set our laser in 2 photon resonance with the transition, and so with these parameters, And of course, varying the laser intensity, we can explore how the spectrum behaves. And the spectrum can be calculated as the final population of the ionic states, as shown by this simple formula. So what we get when increasing the laser intensity is shown here. As we see, more and more Rabi cycles are completed between the resonantly coupled bound states, and meanwhile ionization occurs. And what we see in the spectra is that this dashed line here is the nominal position of the spectrum. So for weak pulses, we see a single peak, and for increasing laser intensity, more and more sub-peaks appear in the spectrum. So the spectrum will get splitted, and it's also shifted with respect to the nominal position. And very importantly, this becomes asymmetric. So all these features of the spectrum, we are interested in the reason what is behind. So how we can explain these spectral features. And for that, we wanted to develop an analytical model to explain these kind of behaviors. And the so-called decoupled resonance approximation, or decoupled resonance picture, we applied, which was found very illustrative in previous works to explain such kind of processes. It turns out that due to the strong coupling with the laser, two resonances emerge, and the energies of which can be obtained by diagonalizing this 2x2 matrix shown here, because this 2x2 matrix describes the resonant transition between the initial and the 2s and 4s states in case of lithium. So by diagonalizing this, we obtain the energies of these emerging resonances, which are present during the action of the laser pulse, and we obtain these energy expressions. So it's real and imaginary part. And here we have the sum of the individual Stark shift, the sigma, and also the difference of the individual Stark shifts included. And as I told you before, the delta, the detuning is set 0 here in our study. So, and this is the 2-photon Rabi frequency. So these energies follow the pulse intensity envelope also. And one can calculate the wave functions, and it turns out that they also, they are superpositions of the resonantly coupled states. These quantities here include the Stark shifts and all the strong field quantities that we are interested in. And it turns out that these expressions become very simple if there are no Stark shifts. So if sigma is 0, then delta S is 0. So it becomes very, very simple. And also here 1 over square root 2 if there is no Stark shift, and so it can be considered a general situation when there are Stark shifts in the system. So to proceed further, we can express the R state from these two wave functions. We can express the R state, and from the R state, we can further express the continuum state. For the details, you can see the cited reference shown here, but from the ionic state amplitude, we can then calculate the spectrum as before. So after doing this analytical derivation, this form is obtained for the spectrum. This looks maybe a bit ugly for first sight, but if you look closely, then it's simple, because it is the sum of two terms here in the braces, which describe the two resonances, resonance plus and resonance minus. And yes, the interference pattern in the spectrum emerges from these two terms, basically. So here we have, of course, the 1 and 2 photon-Rabi frequencies, and this is the imaginary integral, the imaginary part of the resonance state energies, integral of the real part of the energies also here, and this small u is also an integral of the ponderomotive shift of the continuum levels. So this is the so-called analytical model, or the decoupled resonance picture model. I will refer to this later, and it is interesting to see how it compares to the three-state model results. And this is seen in this figure here. So this red curve is the analytical result from the previous slide, and the open circle is the three-state model result. And we see that there is a fairly good qualitative agreement. At least all the main features of the spectrum are recovered by the analytical model, namely the asymmetry of the spectrum, the shifting of the spectrum with respect to the nominal position, the number of subpeaks, the position of the subpeaks are all recovered by this model. So one can use this in further analysis. What is shown here, these intensities are chosen, and the spectra is artificially shifted apart from each other for visualization. So these intensities are chosen such from the previously shown contour plot that the integer number of Rabi cycles are induced. So here 1, 2, 3, 4, and 5 Rabi cycles are induced, and the number of subpeaks are the same numbers in these spectra. What I'm showing here also with the blue curve is the three-state model results when the ponderomotive shift is excluded artificially, and we see that there is a shifting of the spectrum, and we see that the channel closing effect, due to the channel closing effect, we see this shift. And there is not only a shift, but if we look closely, then the interference pattern is modified actually. So this ponderomotive shift is indeed important to include, but maybe most important in the direct non-photon ionization situations than here. So we see all the features, all the important features here. What I want to highlight also is that when we exclude the individual Stark shift from our model, what we get, and this is what we get. So when there are no Stark shifts, then the spectrum is always symmetric, always. So the two sides are the same height, and also symmetric with respect to the nominal position. So this is clear impact of the individual Stark shift, that the spectrum is shifted and the asymmetry occurs. So yes, to further analyze and understand the origin of the spectral features, it is important, it is good to look at the analytical results. And this we can see here. So here I'm showing you again the energies of the resonances, which I showed you before. And one can plot these energies, E plus and E minus. These energies follow the pulse intensity envelope because delta is 0, as I told you before. So the real parts of these energies are shown here by the red and blue curves in the relative to the nominal position in the continuum, and there is also this ponderomotive shift subtracted because of the channel closing effect. So this is what we get. These are the energies of the emerging resonances, and this is the central line here, which is from the same distance from the two curves, from the red and the blue one. So this is the central line. So as we see, these two energies repel each other as the pulse is switched on, and when the pulse has a maximum, they are farthest apart from each other, and so the electrons emitted during the action of the pulse are distributed in a wide energy window, and that's why that leads to the splitting of the spectrum, which is shown here by the green curve. And we see that the center of the spectrum is shifted to higher energies because the center line is shifted to higher energies. And the asymmetry of the spectrum is the result of the fact that the blue curve is more shallow than the red one, and therefore electrons emitted here are distributed in a narrow energy window. That's why the lower energy side of the spectrum is higher, while on the other side of the spectrum here the curvature is larger, so the electrons are distributed in a wider energy window, so the higher energy side of the spectrum is lower in height. So this is how one can imagine how one can trace this spectral features, how one can link the spectral features to the strong field quantities such as the Stark shift and the 2-photon Rabi frequency. And basically that is all I wanted to talk about. And with this I arrived at my summary and outlook. So we could show that the photoelectron spectra following strong field transitions are substantially modified by dynamic Stark shift and also dynamic interference. And the individual Stark shifts they cause the shifting of the spectrum and also the asymmetry, while the multi-peak pattern is the result of dynamic interference of electron amplitudes that are generated in the first and the second half of the laser pulse. We could also show that the ponderative shift of the continuum is important. It not only shifts the spectrum, but it also modifies the interference structure. And these presented models are useful and important, but we are also working on a wave packet propagation approach to fully verify the results shown here, but it's a very challenging task because we need large spatial grids because we want to keep the wave function, the outgoing wave packet, to get the spectrum. And yeah, it's a challenging problem, but hopefully we'll get it soon. And yeah, we need long pulses because to be state selective during the excitation, we need long pulses which have narrow bandwidths, and that's why we need a long grid several times 10,000 atomic units or so. And what we also want to do in the future is to do a quantitative analysis and to extract Stark shifts and 2-photon Rabi frequency values from the observed spectrum. And basically that's it. If you want, later I can show you some preliminary wave packet propagation results which we did for a simple system. So this verifies the validity of the model. But this is not for the lithium, but for a simple system. So finally, I have to acknowledge my colleagues with whom this research has been done. Attila Tóth from Eli Alps was involved, and also my master student who did some wave packet propagation for a simple system. And thank you for your attention.
Thank you very much, András, for this interesting talk. Please, if you have questions, raise your virtual hands. I do not see any hand yet. So, Andras, I understood that you made these calculations for lithium. Did you try, or could you try for molecules similar calculations, or it is too complicated?
Well, we have not yet done such calculations for molecules, but in the literature there are some results for molecules. What we are especially interested in now for molecules is whether we can see such kind of effect for the nuclear wave packet, maybe. So to induce the Rabi transition or in the dissociation of the photofragments.
Okay, thank you very much. I still do not see any hands for questions. So thank you again for your talk.
Thank you.
And let's move to our last speaker. Our last speaker is Torsha Moitra. Torsha, are you here?
Yes, can you hear me?
Yes, I can hear you. Andras, if you can finish your.
Yes, I am.
Okay, okay. So, Torsha, please, you are from Technical University of Denmark, and the floor is yours for your talk, please.
Thank you.
If you can share your screen, yes.
Can you see my screen properly
Yes,
now?
it is very good. It is very good.
Does this sidebar with everybody's picture appear?
It is good.
Okay.
You have full screen. It's good. You can start your presentation.
Okay. Thank you. I'm Torsha Moitra. I'm a PhD student in the group of Professor Sonia Koryani at the Department of Chemistry, Technical University of Denmark. Today, I will be talking on the theoretical modeling of photoionization observables. But before I start, I would like to thank Professor Nagy and all the organizers of the Working Group 2 meeting of the Cost Action Attochem for giving me the opportunity to present my work before you all. Throughout this 3-day meeting, we have heard a lot about ionization processes. So I won't go a lot deep into the introduction of it. Just as a one-liner, I would like to say that photoelectron spectroscopy is the process in which an electron is ejected from the system upon shining light on it. This outgoing electron has a kinetic energy which is equal to the difference in energy of the incident photon and the bound state ionization energy of the system. What we want is to describe this process theoretically. And for that, we must mathematically model all the individual components involved in the process, which is the incident photon, the bound state of the system, which is both the initial n electron state and the final n-1 electron state, and also the outgoing electron. The major obstacle in describing or theoretically computing the photoelectron observables is the need to incorporate correlation effects. We have broadly classified this into two categories. The first is the treatment of the correlation between the bound state. Actually, this is the doable part, more easily doable part. We can incorporate the correlation between the initial n and the final n-1 bound state of the system by using highly correlated wave function based methods like CI, couple cluster hierarchy of methods, the ADC family of methods. So the next is the more involved one, which is broadly termed as interchannel coupling. This can be further subdivided into two categories. The first is the interaction between the individual continuum channels. This is termed as pure open channel states. The next is the interaction between the electronic continuum and the discrete bound excitations, which is termed as the closed channel states. Even though here I have specifically categorized them, distinguished them, but the boundaries between these correlation effects are quite blurred. And throughout my presentation, I will be getting back to the importance of the incorporation of correlation effects in the treatment of both the bound and the continuum states multiple times. The key theoretical quantity that is required to be computed to get photoelectron observables is known as the photoelectron transition matrix element, DIF. It is basically the overlap of the initial n-electron system with the final composite system comprising of the n-1 bound state of the system and the outgoing electron coupled by the dipole operator. 2 slides before, I had shown the essential components for describing the process. And here, this simple expression has them all. Psi in and the n-1 electron bound state is the description of the bound state. The description of the outgoing electron is a part of phi f, and the incident photon is described by the electric dipole operator mu. In principle, we can expand the final composite wave function phi f in terms of the configuration interaction approach of the final state. This has 2 terms. The first term is the antisymmetrized product of all n-1 bound electron states accessible at energy E coupled to the continuum wave function phi eij alpha. The second term is a linear combination of all localized n-electron bases with coefficients C, E, K, I. This second term takes care of autoionizing states. But this full close coupling expression is computationally very, very expensive. Hence, we restrict ourselves to only the first term, and even within the first term, we only consider only one product. So this is known as the single channel approximation, in which the final state of the final wave function is described by the antisymmetrized product of the n-1 bound state and the continuum wave function. This simple approximation comes with its own drawback. This approach lacks coupling between the open channels, and it also lacks correlation between the bound and the continuum channels. So within this single channel approximation, the many particle photoelectron matrix element boils down to the single particle photoelectron matrix element DIF, where phi DIF and the eta DIF is known as the Dyson and the conjugate Dyson orbital. The phi DIF and eta DIF has within it compressed all the information of the bound part of the system. Considering the photoelectron wave function to be orthogonal to all the bound orbitals included in the initial state expansion, the conjugate Dyson term vanishes. And then our photoelectron matrix elements acquires a very simple notation, which is basically just the overlap of the Dyson orbital and the continuum wave function connected by the electric dipole operator. Here, gamma is the component, is the Cartesian component. This photoelectron matrix element is used to compute the differential cross-section d sigma dk. And this is quite a standard equation where alpha is the fine structure constant and omega is the photon energy. Upon a lot of mathematical manipulations, we arrive at this expression. This expression shows that the angular distribution of the photoelectron can be described by only 3 parameters, namely sigma, which is the partial photoionization cross-section, beta, which is the asymmetry parameter, and D, the photoelectron dichroic parameter. Here, I must state that this D should not be confused with the photoelectron transition matrix element DIF. In this expression, the theta is the scattering term, and P1 and P2 are the Legendre polynomials, and MR describes the polarization of the incident light. MR is equal to 0 for linearly polarized light, and MR is equal to plus or minus 1 for left and right circularly polarized light, respectively. With that said, now I will move on to the description of the bound state. I have shown you that we want to focus on the Dyson orbitals. The 1 electron Dyson orbitals are basically defined as the overlap of the initial n electron state of the system with the final n-1 electron state of the system. This reduces to a linear combination of ground state molecular spin orbitals phi p with coefficients gamma p. Now consider a situation where the ionization is solely occurring from the jth molecular orbital. Under this situation, the Dyson orbital is exactly equal to the jth molecular orbital, and the contribution of the jth molecular orbital towards the Dyson orbital is 1, and all other molecular orbitals have a contribution of 0. Under this situation, the ionization energy of the system is equal to the negative of the jth molecular orbital energy. This is also what is stated by the Koopman's theorem. We will use this Koopman's theorem to treat the bound state using Hartree-Fock molecular orbitals and DFT molecular orbitals. But for the Dyson orbitals, we use the equation of motion couple cluster singles and doubles formalism. Within this framework, the bound states of the system are obtained by diagonalizing the non-Hermitian similarity transformed Hamiltonian. In this framework, the right and the left eigenvectors of H bar are not identical, they are distinct. And for this situation, the transition strength SIF is given by this expression. This shows us that the DIF is not equal to the complex conjugate of DFI. Following that, the left Dyson orbital is not equal to the complex conjugate of the right Dyson orbitals. However, both of these two can be expressed as a linear combination of ground state molecular spin orbitals. What varies is the coefficients. The left and the right Dyson orbital coefficients are distinct. And the Dyson coefficients for the ionization from the ground state are given by this expression. Here, T, R, and L dagger are excitation operators, and for RIP or LIP, these operators are not electron number conserving. We have also looked into ionization from excited states, but I won't show any results for that today because we did not have results, experimental results to compare with. Now I move on to the description of the continuum orbitals. And this is the tricky part. The description of the continuum orbitals requires a suitable basis function which will be capable of incorporating its distinct boundary conditions, as well as the continuum orbitals are infinitely oscillating functions. And the simplest approach is to use plane wave or Coulomb wave formalisms. I must also mention here that the generally used Gaussian type or Slater type orbitals are deemed unfit for this purpose. The plane wave considers that after the ionization has occurred, the charged iron core has a charge of 0. This is ideally the case for photodetachment processes. And the Coulomb wave formalism considers that the ionized core has a positive 1 charge. However, actually, the ionized core has a charge something in between these two extreme values. For describing the continuum for a larger molecule, we need a more flexible basis function which will be capable of multicentric linear combination of atomic orbitals. In these 3 days of the meeting, we have already heard a lot about B-spline functions, and we also use the flexibility given by B-spline functions to describe the continuum orbitals. The primitive B-spline functions are described by chi-JLM, which is a product of the radial part 1 by r bjr and the angular part y lm theta phi. What we do is we place a long range large angular momentum expansion at the origin. Say for the water molecule, we place it at the oxygen atom. This takes care of the asymptotic behavior of the continuum orbitals. And we place additional short range expansions at each of the nuclear positions to take care of Coulomb cusps. Even though here I show the expansion for only one hydrogen atom, an equivalent one is present also on the other hydrogen atom. After that, we solve for the continuum orbitals by solving the Schrodinger equation in the angular momentum representation, where the Consham Hamiltonian is given by this expression. For our purpose, we use the LB94 exchange correlation potential, and this choice has been guided by the fact that this is quite widely used in the literature. The tools that we use include the QChem software, from which we obtain the equation of motion couple cluster Dyson orbitals, and we have used throughout the augmented CCPV-TZ basis set. All computations using the LCAO, B-spline, DFT continuum orbitals, and later on for the TGDFT continuum orbitals are implemented in the Tyresia code, developed by Professor Piero De Cleva, who is also a part of today's audience. And the nice part of it is that this Tyresia code will be soon open source. For all plane wave and Coulomb wave descriptions of the continuum, we use the EZ Dyson code. First of all, we tested the accuracy of these individual approaches for describing the bound and the continuum part. For that, we chose to study the 3 lowest energy ionizations of CO molecule. First of all, we keep the description of the continuum part constant to B-spline DFT and vary the description of the bound state from Hartree-Fock to DFT to CC Dyson, which are shown by the blue, orange, and green lines. We see that these are almost overlapping with one another. And this is actually quite expected, as the Dyson orbitals are quite identical to the molecular orbitals considered by Koopman's theorem. And also, the Dyson norm for these ionizations is greater than 0.9. Next, we shift our focus on the performance of the continuum part for the B-spline DFT, plane wave, and Coulomb wave approaches, again keeping the bound state description constant to CC Dyson. This can be shown by the green, maroon, and violet lines. What we see is that B-spline DFT certainly outperforms the other 2 approaches and is usually within the experimental error bars. The simpler analytic approaches can somewhat describe the tail region, the behavior of the tail region with large vertical deviations, but it completely fails near the ionization threshold. And this ionization threshold is basically the fingerprint region and is essential. From now onwards, I won't show any further results for plane wave and Coulomb wave description of the continuum. Next, we looked into the photoelectron dichroic parameter of S-methyloxyrane, which is a prototypical molecule for studying this parameter. We looked into the 6 outermost or the 6 lowest energy ionizations for this molecule. And here we see the importance of the inclusion of correlation in the treatment of the bound state of the system. The Koopman's theorem-based Hartree-Fock molecular orbital shown by the blue lines are quite deviated from experiments or are of completely opposite sign. DFT performs better, but sometimes, like in the case of the ionization from the 11th molecular orbital, it shows larger deviation, whereas coupled cluster Dyson orbitals are almost always within the experimental error bars. Then we looked into a notoriously difficult case, which is the Cooper minimum of argon. It is a signature of the change in the sign of the matrix element depicting the transition into one of the principal continuum channels. It arises due to ionization from the 3p orbital. As the partial photoionization cross-section for ionization from the 3p is much larger than that of 3s, the total cross-section is almost similar to the partial photoionization cross-section for argon 3p. It has been shown earlier that plane wave and Coulomb wave approaches cannot capture this sophisticated experimental phenomenon observation. B-spline DFT, shown by the bold green lines, does capture this process, but the minima is shifted by approximately 15 electron volts towards the lower photon energy region. Due to electron-electron interactions and coupling between the argon 3p and the 3s channels, a Cooper minima is also experimentally observed in the partial photoionization cross-section of argon 3s, which are shown here by the green dots. But B-spline DFT approach lacks correlation in its treatment of the continuum. So we don't capture this process. Somehow, we have to include in our treatment interchannel coupling effects to capture the Cooper minima in the argon 3s photoionization cross-section. The simplest approach of including interchannel coupling effects while still being within the single determinant form for the bound state is the singly excited configuration interaction, CIS, or the Tamm-Dankhoff approximation, TDA. Linear additional correlation may be included via RPA in the linear response framework. This still conserves the essential CIS structure of the excitation. Similarly, the equivalent formulation for DFT is the TDDFT approach, which we use. Here, delta rho is the first order change in the electron density induced by the potential, and chi is the electric susceptibility, and delta V is the first order change in the potential induced by the change in the electron density, and K is the linear kernel connecting the two. In this situation, the full potential is given as the sum of the external perturbing potential mu and the response potential delta V. Now, within our Dyson TDDFT approach, the photoelectron matrix element looks quite similar to that of the Dyson DFT approach, the only difference being that the mu term is now replaced by the full VSCF potential. Thus, the DIF term is the overlap of the Dyson orbital with the continuum wave function connected by the VSCF term. This has been implemented in the Tyresia code, and the results that I will show afterwards are yet to be published. So first thing we did was we revisited the Cooper minima of argon. This is shown by the maroon lines, which uses coupled cluster Dysons for describing the bound part and B-spline TDDFT for the continuum description. We see that the shift that was observed for B-spline DFT by the green lines here is now removed. Also, we are able to capture the minima in the partial photoionization cross-section of the argon 3s. Again, we tested the performance of the Dyson TDDFT approach, and for this purpose, we chose the H2S molecule, and we looked into the two lowest energy ionization pathways of H2S. Here, the Dyson orbitals are shown as the insets, and we see that the major contribution comes from the 3p orbital of sulfur. And thus we expect to see, and experimentally it is also seen, that there occurs a Cooper minima. Again, changing the description of the bound state does not make any difference, because the Dyson orbital is quite similar to the corresponding molecular orbital considered by Koopman's theorem. But on moving from the B-spline DFT to the TDDFT approach, we now locate the Cooper minima at the right position. Following that, we looked into the 5 outermost ionization from CS2 molecule. The 4 outermost ones are quite straightforward, and I thus don't present the results here. These are basically ionizations with Dyson orbitals being identical to the corresponding molecular orbitals, and the Dyson norms are greater than 0.9. The interesting one is the 5th one, the D band, which has an experimental ionization energy of 17.2. By Koopman's theorem, this should be due to ionization from the 4 sigma U orbital. But the ionization energy corresponding to ionization from this 4 sigma U orbital is much, much higher in energy. Incorporating correlation via the UM-CCSD Dyson orbitals, we obtain it at 17.78 electron volts. What we see is that the Dyson norm is quite low. This has been identified as a satellite state of pi U character.
2 more minutes, please.
With that said, I would like to summarize our work, our findings. First of all, the major finding is that B-spline DFT approach outperforms simpler plane wave and Coulomb wave approaches. A general recommendation would be to use, for the bound state description, EOM couple cluster Dyson orbitals, and for the continuum, B-spline DFT approach. However, if we are interested in investigating more sophisticated experimental phenomena, we must use the TDDFT approach. Now, I would like to thank my PhD supervisor, Professor Sonia Coriani, and I would especially like to thank Professor Piero De Cleva, who has been very key in this whole project. The others who have been involved in this project is Professor Henrik Koch and Dr. Aurora Ponzi. Finally, I would like to thank all our group members, especially Rasmus and Marta, who had helped me immensely during the initial days of the project. I would like to thank the funding agencies, Marie Curie European Training Network, COSIGN, and Attochem for giving me the opportunity to present my work. And lastly, I would like to thank you all for your kind attention.
Thank you very much for this very logical presentation and very nice results. Please, if you have questions, raise your hands, your wheelchair hands. I do not see yet any. Yes, Alexander, please.
Okay, it's probably not a question, just a comment, because you mentioned a couple of times that the Dyson orbital is not very much different from the one particle orbitals that you get. This is of course only correct when you don't have correlation effects, or when the correlation effects are not strong.
Yes.
As Koopman's theorem is something very, very low-level approximation, which already indicates that it's the case. So one has to be careful when compare Dyson orbitals with, let's say, simple molecular orbitals, or Hartree-Fock or whatever, Kohn-Sham, especially orbitals, because these are different constructs. And of course, you can have similarities only in the cases when you don't have strong correlation effects. So for example, for the satellite state that you are talking about, I'm sure that the orbitals look extremely different.
Yes, they do.
So yeah.
Also we have looked into some more complex molecules, like a transition metal complex, where they are very, very different. So
sure.
yeah, but these are the simpler examples that I am showing, where the correlation is not playing a dominant role for the bound state.
Exactly, yeah. Thank you, yeah.
Thank you.
Yes, Fernando?
Very nice talk.
Thank you.
Yeah, I am curious to know how much, how expensive is Dyson TDDFT compared to Dyson DFT? Is it orders of magnitude more expensive, or it's just a little bit more expensive?
For doing the Dyson TDDFT, we start with the Dyson DFT. And then the most expensive step is to get the electric susceptibility, which is dependent on the energy. So it is it builds on the Dyson DFT approach. So, and we do get, when we are computing the Dyson DFT orbitals, we do get as a byproduct the Dyson DFT results as well. But I can't really comment on the exact order to which they are more expensive.
Okay, but from what you say, it doesn't seem that it's going to be 10 times more expensive.
No, it is not.
It's just a bit more expensive. So it's really worth trying TDDFT instead of DFT in combination with Dyson.
Yes.
Okay, thank you very much.
Thank you.
Any other questions? Well, if not, I would like to thank all the speakers from this session for their nice presentations. And now we will have some short closing remarks. But after the closing remarks, you will have the speaker sessions as usual. So after we finish here on this Zoom session, we will have the meet the speaker. Okay. Well, for some closing words, I would like to share my screen. I have a very short presentation. I think this is the one. Okay, so first I would like to thank all the speakers of this meeting and chairs for their very important contribution for the success of this meeting. I am very sorry that you could not come to our university, the Babes-Bolyai University, but I have put here the building to see it, how it looks. If you come to Cluj, that just recognize that this is our workplace. Okay, so for the beginning, some statistics. In this session, we had, in this meeting, we had initially 66 registered participants, but in the last minute, 4 other people asked to join. So practically we had 70 participants on this Zoom platform. These 70 participants were from 16 countries, as you see here. And you can observe that Spain is the champion. So from Spain, we have 15 participants, from other countries, less than 10. But 16 countries, all European countries, of course. COST is mainly European network. We had 21 talks from people in different positions, from PhD students to full professors. In my opinion, all the presentations were of very high scientific standards and very interesting. As you have may observed, this was a self-organized meeting, so practically the program was set up by you, because the people from the working group 2 who volunteered to give a talk, they have had this presentation. So it was not I or somebody else who set up the program. It was you, practically. We have self-organized this meeting, and I think that it worked very good, very interesting topics. In a Zoom session, typically we had around 55, 57 participants. Not all simultaneously. You may observed we had around 45, 50 people simultaneously. This was valid for the first 2 days. Today, maybe a little bit less participants were. As you know, our meeting was streamed also on a YouTube channel. Here you have the statistics. In the first session, 36 people were following this YouTube transmission. Second session, 29. After that, less people. I do not have the statistics for today, but probably people have realized that they can watch these YouTube movies later. The first session, for instance, was already watched by 228 people. So 36 followed live, but these presentations could be followed later. And you should know that after this meeting, probably next week, we will move all the registered presentations to the Attochem YouTube channel, and they will remain there, and you can watch your colleagues or yourself also next year there. So these interesting talks will remain on the Attochem YouTube channel. I would like to thank the people who had in organizing this meeting. First, the team from the Babelsberg University. Most of the technical work was done by my colleague Ferenc Járai Szabó. So without him, we could not solve all these technical issues. Katalin Nagy had edited the abstract book, which is on our webpage. And Sándor Bojbé and István Tóth also helped a lot in this organization. And of course, from the Attochem Action Management, I would like to thank Fernando Martin for his advices, to Beatriz for the administrative work, and to Aurora Ponzi, the science communication manager, for advertising this meeting on different channels. Finally, I have put here on this page a lot of question marks. Maybe we should think when we would do the next meeting of the working group 2. I don't know if it can be done face-to-face or virtual. I am very optimistic that till October this year, most of the people from Europe will be vaccinated, and maybe in the fall of this year, we can do also a face-to-face meeting. Let's see how this pandemics evaluates, and how many people will be vaccinated. I have to tell you that I am already vaccinated, so I just wait for the other people to be vaccinated from Europe. So we should do a next meeting maybe in fall of 2021 or in spring of 2022. Let's see if it is virtual or not. What is my request to all of you, think about who could volunteer for the organization. So I am expecting proposals for the organization, either online or face-to-face meeting. About the topics of our research in this working group 2, I have to say again that we have seen at this working group 2 meeting that people are doing research of very high scientific standards. But I have to say that many of us did not listen to Fernando, who have said at the beginning of this cost action that we should study and make calculations for large molecules. Here we had some presentations for about calculation of large molecules, but as you have seen, we had very many results about interaction of atoms or diatomic molecules with these laser pulses. Of course, of very high scientific standard and interesting, but as Fernando have said that we should study large molecules, maybe we could listen to him, and maybe Fernando will have some comment on this. So what are the topics we should study in this working group? Well, finally, I would like to thank for your participation, and I would give the floor to Fernando for some closing words. Please, Fernando.
Thank you, Ladislau, for your presentation. So first, I really want to thank very much Ladislau, Sander, Ferenc, Katalin, and Itzvan for the very hard work they have done to organize this meeting. The organization has been perfect, I have to say. And I realized that these things can be done even without the help of a company. So congratulations for the perfect scientific and technical organization. That's, I think, the most important thing for me to say. Well, apart from that, just to remind you that, well, Attochem is a network in which we aim at exploring how to use attosecond sources to study problems of chemical relevance. So an atom is still chemistry, very simple chemistry, but I would say that atoms are welcome, very welcome, especially because they are ideal benchmarks to treat new methodologies and to find new concepts. But Ladislau is right. I think that during this action, we should make an effort, a collective effort, to move to progressively more complex systems so that we can, at some point, address problems that are closer to chemistry. And to conclude, I just want to remind you a few tools that are available in our action. To benefit from these tools, I insist once again that it's very important to register in the Attochem website. So I will show you very briefly this website. So this is the Attochem website, and here you can find all the information about working groups, Here you have details, and you have here, you know, a place where you can register very easily. You click here, and in 2 minutes you are done. And I insist, it is very important that your group is registered, and also we make a special place for young researchers to register individually. So I encourage you to register, because in this way you will receive news from us about all the different activities. And among these activities, I'd like to remind you that there are already 2 schools that are going to take place very soon. One is a winter school on Attochem technologies that will take place from 8 to 11 March. This is mainly experimental, but we are theoreticians and we should be aware of the latest experimental development. So if you are interested in registering, you are still in time to do it. The deadline to register to that school is today at midnight. So you still have a few hours to do it if you are interested. There is another school that will take place from 22 to 26 March. About new computational methods for Attochem molecular processes. Unfortunately, the registration for this school is already closed because there was an avalanche of applications. And in fact, we will not be able to accept everybody to this school, but our idea is to repeat this school every year. So if you are interested in this school and you cannot attend this year, you can do it next year. And so keep tuned to our website, where you can find, as you see here, the news about the different events. I'd like also to remind you 2 important things. One is that we will have a special issue in computer physics communication. You heard about that in Jimena talk this morning. So if you are developing software that is relevant for the topics in this cost action, you are welcome to submit a paper, and knowing that it is not only a paper what you have to submit, but you also have to submit software. And the deadline for this will be the fall of 2022. I want to encourage you to apply for grants that are called Inclusive Target Country Conference grants. These are grants that cover fees and travel expenses to attend conferences. Nowadays, traveling is not possible, but there are many conferences that still require to pay a fee, even if they are organized online. And so you belong to one of these inclusive target countries, and you have the list here in the cost in the Attochem website. You can apply for that, and we have funding to support your attendance. And also, I want to encourage you very much, if things go on improving in Europe, as it seems to be the case, I encourage you very, very much to apply for short-term scientific missions, which are devoted mainly for collaborations between different nodes of the Attochem network, in which a researcher applies for some funding and can spend from 1 week up to 2 months in one of the Attochem nodes to develop a scientific project in collaboration with another group. So this is ideal for PhD students, but of course, it's also a good thing for more senior researchers who want to spend a short period of time somewhere else to develop new ideas with other collaborators. And with this, I think I finish. I conclude by reiterating my deep thanks to Ladislao, Naji, and his team for organizing this. And I hope to see you all in future Attochem events. Thank you very much, and goodbye.
Thank you, Fernando. So please do not forget about the meet speaker opportunity. So you can go and talk with the speakers. So have a nice weekend and goodbye.
Bye.
Bye.